Hello, calculus students. Today we're going to continue section 3.3 and look at the definitions and derivatives of a couple more of the trig functions, tangent x and secant x. Hopefully from pre-calculus you remember that tangent x is defined to be the sine of x divided by the cosine of x, and that the secant of x is defined to be 1 divided by the cosine of x. So if we want to find the derivative with respect to x of tangent x, we're really just finding the derivative with respect to x of sine of x divided by cosine of x. So we want to use the quotient rule to define the derivative of sine x divided by cosine x. So that's the bottom, cosine x, times the derivative of the top, derivative of sine x, minus the top times the derivative of the bottom over, that is divided by, the bottom squared. So we have cosine x times the derivative of sine x, or cosine x, minus sine x times the derivative of cosine x, so that's, again, a negative sine x. Now, these parentheses right here are extremely important. They're around negative sine x. We're not subtracting sine x, we're multiplying by negative sine x. Again, all divided by denominator squared. Okay, this equals cosine x times cosine x is cosine x quantity squared. A negative times a negative is a positive, so this becomes plus sine x quantity squared, all divided by cosine x quantity squared. Now, hopefully you remember a trig identity from pre-calculus. The identity is the cosine of x quantity squared plus the sine of x quantity squared. This quantity is equal to 1. The cosine of something squared, quantity squared, plus the sine of that thing, quantity squared, is always 1. So I can replace that numerator with 1. That's an identity from trig. So what I have is 1 over cosine x quantity squared. But I can write that as 1 squared because 1 is 1 squared divided by cosine x quantity squared. And I can write that as 1 over cosine x, that quantity squared. Recall that a over b quantity squared is a squared over b squared. I'm using this. A squared over b squared is just a over b quantity squared. That's what I'm using. Okay, but 1 over cosine x is secant x. This is sometimes written like this. Realize that these two things, secant x quantity squared and secant squared x, are just two ways of writing the same thing. So now I have my derivative shortcut. This is in your book. It's on page 193. And we now know that the derivative of tangent x is secant x quantity squared. You need to understand where we get this, where it comes from. It comes from quotient rule, but you also need to commit this to memory. Now let's jump down. There's a chain rule version of this shortcut. The derivative with respect to x of tangent of f of x by chain rule would be the derivative of the outside, the derivative of tangent, which is secant squared, times the derivative of the inside, so times f prime of x. Again, each shortcut has a chain rule version. We see f of x instead of x, so we know we have to use chain rule. So we multiply the derivative of the outside, which is secant f of x quantity squared, by the derivative of the inside. Okay, now let's find the derivative with respect to x of secant x. We know that secant x is just 1 divided by cosine x. So again, we use quotient rule, which says the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So we have cosine x times 0. The derivative of 1 is 0. Minus 1 times derivative of cosine x is negative sine x. Again, these parentheses are extremely important. So I have 0 minus a minus. So I have 0 plus sine x. So I just have sine x in the top. In the bottom, I've got divided by cosine x quantity squared. Now, if I want to, I can write this as sine x over cosine x times 1 over cosine x. Let's see if that's right. To multiply fractions, you multiply the numerators. So sine x times 1 is sine x. Multiply the denominators. Cosine x times cosine x is cosine x quantity squared. Why did we do that? Because sine x divided by cosine x is just tangent x. And 1 divided by cosine x is secant x. And the derivative shortcut in books is always the derivative with respect to x of secant x is secant x tangent x. So again, this is in your book on page 193. You need to understand where it comes from, but you also need to memorize it. Now, there's a chain rule version of this shortcut also. I know that the derivative with respect to x of secant x is secant x tangent x. What if I have an f of x instead of an x? What if I want the derivative with respect to x of secant of f of x? Well, I have an inside and an outside function, a composite function, so I need chain rule. Derivative of the outside, derivative of secant is secant tangent. But chain rule says I have to also multiply by the derivative of the inside. So I have to multiply by f prime of x. Okay, so let's just look at some examples. If I want the derivative with respect to x of 3 tangent x plus 2 secant x, well, that's the derivative of a sum. So I need to take the sum of the derivatives. Now, I need constant multiple rule. This 3 is a constant multiple. There's no need to use product rule for 3 tangent x. I can just bring the 3 out front. But I've got to multiply by the derivative of tangent x, which we learned just a minute ago was secant x quantity squared. Again, the 2 secant x, the 2 is a constant multiple, so I can bring it out front. Now I need the derivative of secant x, but I just learned that that was secant x tangent x. This is my answer. If you want to factor a secant x out, that's fine, but it's not necessary. Okay, derivative with respect to x of tangent of 3x. I've got an outside function, tangent, and an inside function, 3x. So I need chain rule. The derivative of the outside, the derivative of tangent, is secant squared. So the derivative of tangent is secant squared. That's the derivative of the outside. But I've got to multiply by the derivative of the inside. So I've got to multiply by the derivative of 3x. So I get secant 3x quantity squared times 3. We usually write that as 3 secant 3x quantity squared. If you want to write it like this, secant squared 3x, that's fine. Either one of these is the correct answer. Okay, so I want the derivative with respect to x of secant 3x. Again, I need chain rule because I have an outside and an inside. The derivative of secant, the derivative of the outside is secant tangent. The derivative of the inside is just 3. So I get secant 3x times tangent 3x times 3, and we usually write that as 3 secant 3x tangent 3x. Notice that I just got through using these two chain rule versions of the shortcuts in these previous two examples. I don't have to go back and use the quotient rule here and here because I already know what my shortcuts are. I've done this work up top once. I don't have to do it again. All this work up top using the quotient rule gave me these shortcuts, which I now remember and use. Okay, another example. Derivative with respect to x of 5x secant x squared. This is a product. So, product rule says the first times the derivative of the second plus the second times the derivative of the first. Now, if I wanted to, I could have done what I did, which is view the 5x as one factor and then the secant x squared as another factor. Or I could have used constant multiple rule and brought this 5 out front. But I chose just to group the 5 with the x and deal with that as one factor. Okay, so I've got 5x. Want the derivative of secant of x squared. So that's a composite function. You've got an outside and an inside. The derivative of the outside secant is secant tangent. And I've got to multiply by the derivative of the inside, by the derivative of x squared. I'll just write my road map here to keep from doing too many steps at once. So I have plus secant x squared times derivative of 5x is just 5. I've still got some derivatives to compute here. I'm trying not to do too many steps at once. Derivative with respect to x of x squared is 2x. I'll bring this 5 out front. And so I have 5x times 2x is 10x squared, secant x squared, tangent x squared, plus 5 secant x squared. I could factor out a 5 secant x squared if I wanted to, but that's not necessary. Okay, final example. Tangent, or the derivative with respect to x of tangent x cubed. So I have an outside and an inside function. So I need chain rule again. The outside function is x cubed. The derivative of x cubed, I need power rule. That's 3 times my variable squared. This is the derivative of the outside, but I've got to multiply by the derivative of the inside. So I've got to multiply by the derivative of tangent x. So I get 3 tangent x quantity squared. The derivative of tangent x is secant x quantity squared. I could write the answer like this. Either one is just fine.